to Sigma research session number 2. We have 6 amazing talks from a variety of different fields. We're going to hear about data interaction game, talk about data citations, 2 talks about privacy, and a talk on authentication and access control, and a talk on practical and secure substring search. Okay, so without further ado, let's go to the first talk. It's going to be given by McCamish. Thank you.
Hello everyone, my name is McCamish and I'm here to talk about my work and the paper. There we go. Alright, so titled Data Integration Game. Okay. So we're going to start off with an example here. We have a user and a database, and this database contains students and their names and the department they belong to and some grades. And this user wants to find some information out of this database. So the first thing that the user does is they're going to think of what they want to find from the database, and we call this the user's intent. So in this case, the user is thinking about finding Carrie Smith in the CS department. Typically, what they do then is they're going to express this intent that they're thinking about with a query. In this case, this would be the SQL query that they would need to enter to get the tuple that they desire out of the database. The problem is that most users don't actually know the structure or content of the database, and they don't really know formal query languages either. And so they prefer to use keyword queries. And so here's the keyword query that the user enters for this database, just the last name Smith. And this is nice because now the user doesn't need to know the content or structure of the database, and they don't need to know any formal query languages in order to query the database and try and get their intent that they're looking for. The problem, however, now is that the database is going to have a little bit of a difficult time answering the user's keyword query because keyword queries are a bit vague. So here, when the database receives Smith, it's going to return Sarah Smith and John Smith to the user, which isn't what the user is looking for. So from that interaction, though, the user can actually learn, and they reformulate their keyword query, so they're making it a bit more specific now. So instead of just Smith, they're saying Smith and CS. And because of that, the database system is able to find the tuple that they're looking for and return it to them, satisfying the user. Okay, so the database system can also learn, and so in this case, we have a different user that enters the keyword query Smith, very generic, and before the database system couldn't answer it, but now, after maybe some interactions, it's been able to learn that when the user enters this keyword query, I need to return Carrie Smith in CS. Okay, and the database system is able to learn through feedback from the user, such as clicking on the correct tuple when it's returned to them. So this interaction between the user and the database system can naturally be modeled as a game between these 2 rational agents. Okay? And both of these agents are going to learn and adapt. The final goal of this interaction is they both want the user to get the desired information. Right? And the database system does this by it needs to understand the intent behind the user's queries, and the user needs to be able to express what they're thinking about, their intent, in a way that the database system is actually going to be able to understand it. So we have a user strategy, which is how their intents are expressed using queries, so what they're thinking about finding is expressed using queries. And then the database system strategy is going to be how to map those imprecise queries from the user to the actual desired queries. And the payoff of this entire game is the amount of desired information the user receives. Alright, so over here we have on the right, let me use this. There we go. Okay, Okay, so we have our intents over here, and this is what the user wants to find from the database, okay? And so, as we talked about, they need to decide how to express these, and in this case, the user is going to express their intents with a couple different queries here. And so, if we're looking at intent 2, the user wants to find Sarah Smith in the CE department, they're going to express that with two different queries, Smith CE or Smith. And this is all in this user strategy up here. This is a row stochastic mapping from the intents to the queries. So with intent 2, we have the user is going to have a 50-50 chance of submitting either query 1 or query 2 to the database system. So the user can also have multiple intents mapped to the same query. So here we see for all of the intents, there's some probability that the user is going to enter query 2. So for intent 1 and 3, it's 100%. For intent 2, it's 50% that they'll submit query 2. And this is kind of one of the reasons why it's difficult for the database system to find exactly what the user is looking for behind the query. Because they may submit a query and they may say submit Smith, but it could be any one of these three things that the user is actually looking for in the database system. Now, the database system is going to receive queries from the user, and it needs to decide what the user's actual information needs is. And it does this by, this is the database system strategy here, which is a mapping of the queries it receives to the intents of users. And here we have a list of intents. This is just data log representation of it. So we have, it receives Smith and CE, and it's going to map with 100% probability E2 here, which would return Sarah Smith and CE to the user. Okay, so we have these two strategies, the user strategy and the database strategy. And to calculate we have a payoff function which is going to calculate the expected effectiveness of communicating all of the intents correctly. So here is our formula for the payoff. This pi here represents the prior over the intents, so that's the probability that a particular intent will be queried for. And then we have the U and D are for the user and database strategies respectively. And then we also have a satisfaction metric here, and we can calculate that using any satisfaction metric, and we use user feedback in order to calculate that, such as the user clicking on return results. Alright, so the first question that we need to ask is, what algorithms effectively model user learning? So research in psychology and empirical game theory has shown us that humans actually exhibit some reinforcement learning behavior, right? And there's two main components of reinforcement learning. We have exploitation and exploration. So exploitation means that the user is going to select a query based on its past success. So the more successful a query has been, the more likely that the user is going to select it again. And then exploration means that the user may try new, less successful queries, hoping to get a better payoff in the long run. So they might sacrifice some immediate payoff. They submit a query, it doesn't do so well, but maybe over the long term it does better. So we've evaluated multiple different learning algorithms and they come from empirical game theory. And they kind of differ in a couple different respects. And the first of which is how much they consider past interactions, which is going to be short-term memory and long-term memory. Short-term memory means that these algorithms only consider the most recent interaction, whereas long-term they can consider all previous interactions or most of them. And then they also differ on the degree to which they exploit or explore, so that bit that we talked about earlier, and then how they reinforce their learning algorithms. So whether they're going to use direct payoff or maybe a discounted payoff, but how they're going to reinforce what they learn. So this is the setup for the experiment that we performed. We have a Yahoo interaction history of approximately 200,000 interactions for the results that I'm going to be showing you, which is about 101 hours. And each interaction is going to contain some information that we use. So it contains what query the user entered, a timestamp, a user ID associated with them, the URLs that were returned, and which ones were clicked, and which clicks are not in the way. So we have a way of filtering out which one were just noisy clicks. And this actually effectively models database users, as our users don't actually know the schema of the database. Okay? And we designed this experiment. We train and we test over all of these learning algorithms on how accurately they're going to predict what the user will do next. Okay, so here's the results for that. We have our algorithms over there on the left, and this is the mean squared error here, so lower value is better. And it turns out Rothanev is the best here. And what Rothanev does is it reinforces a query based purely on its payoff. And it's going to pick a query randomly to express an intent proportional to the probability, it's going to have a probability proportional to the previous successes. Okay? And this is the exploitation part of Rothanev. So the more successful a query has been, more often the higher probability that it will be submitted again for that intent. It also is going to pick queries randomly every once in a while. This is exploring, so it models how the user can maybe search for something but try something new, and so they're going to submit a new query. Okay. So the next portion is going to talk about how the database system should actually learn and adapt its strategy. So current search engines use reinforcement learning algorithms, such as UCB1 is a pretty popular one. However, they assume that the user doesn't learn to change their strategy. So the first thing that may come to mind as well, it's pretty intuitive then. If we have a user in a database system that share the same interests, and we assume the user does learn, then that's great. That can only help, right? And so these current online learning algorithms should be able to work. However, that's not true. They don't. There's a couple of different reasons. One is there are many games in which players learn to collaborate. Both of the players are learning and collaborating. However, the payoff is actually going to decrease over time. Okay? That's because these players can get trapped in a cycle. And then the current learning algorithms actually assume that users don't learn and they have a fixed strategy. So when they're submitting a query, they're going to always want the same thing for it. And what this leads to is that these algorithms can't actually discover new intents, and so they can't adapt in a dynamic environment when the user is learning. Right, so I'm going to walk through how our algorithm works through a toy example. So this is just a small toy example here. So we have another database containing some students again, and it's going to be the year, department name, and what school they belong to at the university. So we have a query, Smith, that's going to come in. And our database is going to start off, our algorithm is going to start off with a reward matrix. And the reward matrix, what that does is down here, it keeps track of all the reward accumulated thus far. So for this example, we're just going to initialize it to even, so it's all just going to be 1. Okay. And then we construct a database strategy from this reward matrix. Alright, so here we have Q1, E1, so the query 1 that's coming in Smith, and E1 is Carrie Smith. And we calculate the probability of the database strategy, which the numerator is going to be the reward value in the same cell in the reward matrix, and then the denominator is just going to be the sum of that row. Okay, so we start with 1 as the numerator, and then we have 1/3 for the sum of that row, and so we get 0.33 there initially. And then the rest of them just fill out the same because the reward matrix is equivalent across the board. Now, user is going to submit a query, and the database, let's suppose that it returns E1 here. So it's returning the first tuple here to the database, or to the user, with a probability of 0.33. Now, this is a bit different because we don't actually do any top K, return top K, based on the ranked scores here. It's going to be purely based on probability. And let's say that what was returned to the user, E1, actually satisfied them for the query they submitted, Q1, right? So, and the user is going to indicate this to us through some feedback. So they clicked on the result and said, yes, this is what I want. And we're going to add 1 to the reward matrix here. And so our reward matrix, that cell actually goes up. So now it's 2. And now that the reward matrix is updated, we update our database system strategy. So the database strategy is going to go up. So you see Q1, E1 here increases to 0.5 because now it's 2 over 4. And then what's nice about this is the E2 and E3 are implicitly decreased. So now they become 1 over 4. So the probability of the other intents went down when we reinforced E1. Okay. Now, this is actually pretty impractical to do in practice, where you have, a tuple for every intent up here. So we, in reality, we keep features for all the queries and intents. An example of that would be engrams for all the queries and the content of the tuples. Okay, so we have some theoretical guarantees, and this is a theorem that's in our paper, and it's if both the user and the database system are actually using the Boffin-Eric method, then the payoff of the game is going to remain the same or increase. So we are not going to actually decrease in the payoff. And this also holds true if the user isn't learning. Okay. Now, when we have keyword queries over multiple tables, we may have to join those tables, and that can be quite time-consuming. So here we have another keyword query, Smith CS, and we have 2 tables, department and students. And in order to find the student that's in the CS department, we have to join these tables together. And so we process this keyword query over it, and we get a hit on CS on the first tuple in department, and a hit on Smith in both tuples and students. And so we join them together. Okay, and we have to fully materialize the join, and then we sample over the fully materialized join table here. And the database system actually may have to do several joins, many different joins, because it doesn't know exactly what type of join the user needs. So the first issue is solved by using reservoir sampling, which eliminates the need to actually materialize the full join. We can simply sample as we're joining tuples, so we never have to store the entire join. And then the second problem, that's still kind of slow, and so we further improve it by implementing what's called Poisson-Olkin sampling algorithm, and that instead does some sampling of the individual tuples beforehand. So if we have Smith and CS here, we still grab CS here, and we don't grab E, and then we grab Carrie Smith, but we don't grab Bob Jones here. Okay? And so what we do is now we're left with just a single tuple down here after our join. And so this is actually joins significantly fewer tuples, and there's a lot more details in the paper. Okay. I'm running out of time, so I'm going to skip that. And I'm going to just show you the results of our algorithm real quick. This is UCB1, and this is X is number of interactions we got up to 1 million, and this is the mean reciprocal rank. And then red is the default that has a slow startup, so then we do green and yellow here, which is just increasing the amount of reinforcement. And then for our join, Poisson-Olkin actually significantly improves from reservoir. And so database systems should use some randomized learning algorithms. We should definitely take into account that users are learning and adapting when interacting with database systems. And we have an efficient sampling algorithm to implement actually our learning algorithm. And the next steps is we want to do some data integration between a bunch of different tables interacting in a similar way. All right, thank you.
We have time for a couple of questions.
So when you consider interactions, so what's did you do any user study to see how many number of interactions a user needs to satisfy that user?
Oh, I see. Before the database system can actually learn from that particular user what they want?
Yeah.
We didn't look into how many interactions, but our algorithm usually pays off in the long run, so it takes some time.
Okay. Thank you.
Yeah, thanks a lot. Related to the question, so like looks like we have to get some information about the particular users to learn like their information needs or intent, and like can we use some information from particular user to like other user, and like because like we have to get information and it's only useful when we have some enough information about the user. So is it only useful for very complex queries, or can it be used for simple queries about using other users like interaction information?
I see. So complex and simple queries, they can answer both of them. As far as like distinguishing different groups of users and what they may want, that is something that can be solved with a couple different database strategies. But in general, for this study, we look at users as kind of a collection, a group of users as one.
Our next talk is about data citation.